Welcome and thank you for joining us today for System Effects and Design presented by Verantis. I'm Mary Rusnak, the Marketing Director for Verantis, and today I have John Tonkowitz, Senior VP of Technology with me. While we wait for everyone to join, I'd like to go over some basic information about our webinar platform and the PDH professional development hours that are available. Our presentation today is very detailed, so I'm going to go through this as quickly as I can, and then we can begin. Our webinar platform is completely interactive. All of the windows can be minimized, maximized, or resized, so do what you need to do to make it work for your platform, for your screen size and all. A recorded version of this webinar will be available later on demand, and all the activity or interactivity that I'm going to talk about here will remain. On the bottom left of your screen is the media player. If for any reason you lose your sound, this is one of the areas you should look first to make sure you just don't have it muted. Otherwise, you can also look at the question mark, and that can help you out with technical difficulties. Also on the left-hand side is the Q&A widget, and that's basically where you will submit any questions. To keep ourselves on track, all the questions are going to be held until the end of the presentation, but you can submit your questions at any time. If we don't get to your question, don't worry about it. We will contact you later and make sure that your question is answered. So feel free to just keep pushing those questions forward to us. Also, on the left-hand side, you will see the resource list. This is going to be available for viewing and printing at all times, and this is regardless of whether it's live or on demand. One of the resources that you might find interesting is the System Effect and Design Guide. This is something that you would probably find very useful if you were going to be taking the quiz at the end. Slides of the presentation are also available, and I have a little sheet there that talks to you about the professional development hour state information. Right now, Verantis is able to offer these PDH hours for 32 states. One other thing that you'll see is there is a link to the Verantis webinar page. Verantis has one more PDH webinar this year that's going to happen next month. It's fan installation and maintenance, so feel free to go on over and register for that if that's something that sounds interesting to you, as well as we have about 4 or 5 right now that are available on demand. So remember, if you get to the end of the year and you realize you're down and you need to pick up a couple more PDH units, come on back. You can take some of the on-demand webinars that we've done in the past. Along the bottom are widgets. And basically, if you hover over them, they'll tell you what they are. There's a couple widgets that can help you with if you want to share this broadcast here via social, if you want to email us directly. Just take a look. You know, there's also a survey button, and we'd really appreciate any feedback you can give us here at the end of the presentation. Now, at the end, there is the test and tracker widget, which is the yellow widget and the green one. The yellow one is where you would actually find the status of your certification. This is where you're going to find out if you've done everything you need to do to get the certificate. It's also where you come back to print later on. And the last widget is the actual quiz that you have to take. Let's talk about today's webinar. The value is 1 PDH professional development hour or contact hour. You must be present for at least 50 minutes. This is both for our live version and our on-demand version. If you get interrupted and or need to leave, you can come back to the on-demand version later on to complete whatever it is you need to complete. You must complete and pass the test, and we're looking for basically 8 out of 10. Not all states require this, but this is something that we require to make sure that you've gotten a good fundamental grasp of what it is that we presented to you today. When you are done with all the requirements, you need to print your certificate, and you're going to go back to that one widget that I talked about. And if you, for some reason, aren't able to print it right away, you can come back and print it later during the on-demand version. Verantis is going to keep records of this for 6 years, and we recommend that you keep your own record log. A lot of states offer a spreadsheet that you can download for yourself to keep track of all of your hours that you're doing. So I would recommend you take a look at your own state's guide and see if they offer something like that. If you have any questions, just feel free to contact me. There's several ways to do it, via the buttons on the bottom or even through your initial registration. So We're going to move on to the presentation now. I'm going to pass this on to John.
Thanks, Mary. Thanks to everyone for attending today's session. Today's webinar, we're going to be covering system effects as related to ventilation system design. Specific topics will include definition, causes, and impacts of system effects, plus best design practices and some real-world examples. We'll take a look at some photos. So what are system effects? System effect or effects, sometimes it's used singular or plural in the industry, is a common term used in the air-moving industry to describe the change in ventilation performance due to the interaction of the individual elements of the system. That's a pretty obscure definition, and as we go through it, I think you'll see how it relates. As specifically related to fans, the term is used to describe certain inlet and outlet flow conditions that can adversely affect the fan performance. System effect occurs in a ventilation system when two or more elements are located within close proximity to one another. It could be dampers, elbows, transitions. The non-uniform airflow patterns, the turbulence that's produced, result in a loss of energy that typically exceeds the expected loss for the individual components themselves. So we have a poll question up there right now we'd like you to take a look at and answer. Have you ever been involved with a ventilation system where the fan was not achieving the catalog performance? I'll give you a few seconds to answer that. Okay, good. See from the results that most of you have been, 3/4 of you have been involved in having a ventilation system that didn't perform as required, and that's possibly and probably due to system effects. So the impacts of system effects are basically decreased flow, more energy required to achieve the required performance, increased noise, intensified vibration, in some extreme cases, premature fan impeller or bearing failure. The effects noted are due to the increased turbulence and increased static pressure losses for the system. So at this point, I'd like to spend some time talking about basic ventilation design. Energy loss in duct systems is due to primarily two things: friction losses and dynamic or turbulence losses. This illustration shows the flow profile for fully developed or undisturbed flow of air at constant velocity in a straight section of ductwork. The typical profile is a result of the drag or friction loss of the air contacting the walls of the duct. So the true velocity internal to the ductwork is slightly lower at the walls of the duct than it is in the center of the duct. So for undisturbed flow, the energy loss can be described by this following equation. It's a function of the velocity, the duct dimensions, and the surface properties of the ductwork. most times using this type of equation isn't really necessary because there are many software tools, engineering tables, etc. available that provide easy determination of friction losses based on the duct size and the material of the ductwork. So this is just an example of a table that provides friction loss based on different velocities and different sizes of duct. So the second type of loss is due to turbulence. This is created after an obstruction or change in direction in the ductwork. This results in swirl and eddies that you can see at the bottom section of the elbow, the exit of the elbow. And it requires additional duct length after the disturbance to reestablish a uniform flow profile. So dynamic losses or turbulent losses are caused by elbows, transitions, bends, and the other components, dampers, that are located in the direction of flow. Turbulence losses can be defined by an equation also where the Fn in this particular equation is the turbulence coefficient. There's different coefficients for different types of elements in a duct system. Again, in many cases, you do not have to typically calculate the turbulence losses for each individual elements. There's a variety of tables and information available, Industrial Ventilation Guide, ASHRAE Ventilation Guide, that provide you the amount of turbulence loss of a particular component, but put it in terms of equivalent straight ductwork. So in this case, the example is a 12-inch diameter, 1.5 radius elbow. And you can see that that has the same total loss as 25 feet of straight 12-inch duct. So, it illustrates how turns and changes in direction can really add significant loss to a system. So now I'd like to go through some best practices for duct design, which may seem pretty obvious to many of you that have done duct designs before, but surprisingly, in many systems that I've seen, aren't always utilized in the real world. And they can definitely magnify the impact of system effects. So they're illustrated here are the many different ways that you can design a 90-degree elbow. Sharp changes in airflow, as shown here, can have significant dynamic losses. But as noted on the drawing there on the right, the addition of properly designed turning vanes to help direct the flow change can significantly reduce the losses, in this case by over 85%. So here's another illustration using computer flow modeling to illustrate that point. You can see that the green areas indicate uniform flow. Illustration on the left with no turning vanes has significant high velocity zone shown in red after the turn. Small turning vanes have improved that, and then the right illustration, the larger turning vanes have almost eliminated the higher velocity zones. Smooth radius elbows can accomplish the same thing without the use of turning vanes. And the larger the radius of the turn, the lower the dynamic losses. So in the prior table showing equivalent lengths of duct for elbow turns, it illustrated 1.5 radius, 2 times radius, and 2.5 times radius. As the radius gets larger, the overall turbulent losses become smaller. So to go back to our prior slide showing the different types of elbows, the two that are illustrated with the red X really should never be used. Sharp 90-degree turns, no turning vanes whatsoever, extremely high energy loss. Wherever possible, maximum radius should be used, or radius with turning vanes where possible. Branch connections are also another area that can have significant dynamic loss if not properly designed. The illustration here on the left shows that in some cases turning vanes are not always the answer, because if they're not located in the proper place, they can actually provide more disruption than they help. So it's better to actually provide slight angular turn whenever you're going into a branch. And similar to the example with the elbows, providing a radius can also accomplish the same thing and reduce the turbulent loss coefficient through a branch. Most designs for branches use a straight entry with an angle in the direction of flow. The smaller the angle of entry, the lower the losses, because again, reducing turbulence and trying to maintain a smooth airflow profile as much as possible. You note from the table here that the worst arrangement for a branch would be 90 degrees or a T connection. Transitions can also have a similar effect. The smaller the angle of change, the less disturbance to flow, which reduces the energy loss. This particular slide would show contractions going from a larger duct connection to a smaller. And there will be a loss associated with doing that. But the more gradual the angle of the duct change, the lower the loss. Just a comment, if these were expansions, for expansion, typically there's a pressure regain. And in that case, you'll achieve a higher regain in pressure by, again, having a shallower angle. the more drastic the change is, the more detrimental it is to the system. So when designing ductwork to the maximum extent possible within given space constraints, because that's always the concern, you should always try to select a duct arrangement, duct fittings, etc., to minimize flow disruption and approach a uniform profile. So the reason that I wanted to go through some basics of ventilation design is because best practice in terms of the duct design itself definitely has an impact on system effects. So we'll talk a little bit about that now. So here's a basic example of a duct run with two changes in flow direction. The 45-degree turns are 1.5 radius mitered elbows with a length of duct in between. So from just looking at this, it would appear reasonable to assume that the static pressure loss for this arrangement would be based on the dynamic loss of the two elbows plus the friction loss for the straight run of duct. But if those elbows are located too close to each other, a system effect is possible. So when you look at potential system effects for ductwork, method of calculation to determine the pressure loss incurred by this configuration, two elements at a time. So you calculate the pressure loss associated with each fitting as if it occurred by itself, and then you have to sum those and you multiply them by an appropriate system effect coefficient. So these coefficients are available. I think I gave an example there at the bottom. Chapter 21 of the ASHRAE handbook has a number of them for different types of elements in series. So let's take a look at that and those coefficients and what impact that can have. So you can see from this table that if the distance L between the two elbows is small, system effect could increase the overall losses through this section of ductwork, just this one section, based upon the K coefficient. For a length to diameter ratio of 4, the energy loss will be 30% higher, 1.3 times the expected if it was just looked at based on the individual components. So this is why I spent some time going through the basics of ventilation design, because the proper design of the individual components such as elbows and branches is very important, because system effects will be magnified proportionally based on these types of factors. For example, a similar arrangement with two sharp 90-degree elbows instead of the two 45s would have a much larger increase in static pressure loss. So as far as system effects in the ductwork, proper determination of the total pressure drop for any ventilation system needs to include the evaluation of potential system effects created by the location, proximity of various duct components. If you don't take this into account, The static pressure requirement that's going to be specified for the system could be much, in reality will be much higher than what the calculations would indicate. And then just in general, to minimize system effects, try to space out components to the maximum extent possible. Now we'll talk about system effects as related to fans. Fan performance is typically based upon the specific test arrangement as specified by the fan manufacturer, which in most cases is per the AMCA standards. Test arrangement shown here includes sufficient inlet duct length to provide uniform flow into the fan and unobstructed flow at the outlet. Non-uniform flow coming into the fan due to improper duct connections will result in reduced efficiency of the fan and performance deviation from the fan's rated performance. This is separate from what we discussed as far as system effects in the ductwork upstream. This is where the fan itself becomes one of those two components that you're looking at. For example, combining an elbow with the fan and how that relates to creating a system effect. And what's really happening is that the interaction of the air and the obstruction at the inlet or outlet causes additional energy losses, which again we're defining as system effect or system effects. So the most common causes of poor fan performance due to system effect are non-uniform inlet flow, where you have an elbow, turning vanes, possibly a transition, air straightener, or some other element of the duct system located too close to the fan inlet. Another is if the airstream coming into the fan is swirling, especially if that swirl or that turn is in a direction opposite to the direction of the rotation of the impeller. Same holds true to some degree for the outlet connections. Again, elbows, branches, turning vanes, dampers, anything located too close to the outlet can create and enhance a system effect. So this illustration shows a basic fan performance curve and a related duct system curve. Point number one is the expected operating point for the fan. However, due to system effects, the actual airflow resistance of the duct is higher than what was designed for. In this case, we're looking at a fixed speed fan. So the operating point has to shift along the fan operating curve, and it shifts over to point 4. Now that's going to be a lower flow point and a higher static pressure point on the curve. So the only way to achieve the original design flow with the new higher system resistance due to system effect is to increase the fan speed, which would take you to point 2 on the system. So let's look at a specific example here, which maybe better illustrates the actual impact in terms of flow and energy usage. The example here is 15,000 ACFM flow, 14 inches static pressure. That's the original design basis. We're going to just pick a number of 25% system effect. So this would be based upon the ductwork upstream, elements located too close to each other, causing additional turbulence. Could be based on elements, again, located too close to the fan inlet or outlet, causing the same kind of turbulence. Well, what that indicates is that the actual system requirements are not 15,000 at 14 inches. They're going to be 15,000 CFM at 17.5 inches. So this is the point 1, which is highlighted in the red box, is the original design point used for the fan selection, 15,000 CFM at 14 inches. Because again, we're looking at a fixed speed design, and due to the additional resistance in the ductwork, what's actually going to happen in the field is the fan performance point is going to move to the left up to point 4. At that point, static pressure is higher, 14.8 inches, and the flow is 13,800 CFM. So we have about a 1,200 CFM reduction in flow. And where we truly want to be now, in order to get back to achieving our 15,000 CFM ventilation rate, is at point 2, which is located on a new system, duct system curve, and also requires a higher RPM of the fan to shift the fan curve up higher to that point. So that intersection is at point 2. So let's look at the impacts in terms of energy and RPM on the fan. So we started at 15,000 ACFM, 14 inches static pressure. The brake horsepower would be 42.1 for this particular fan, and the operating RPM would be 2,095. The actual performance that we're seeing in the field is 13,800 CFM, 14.8 inches static pressure. The brake horsepower is actually slightly reduced. We're at a slightly different efficiency point. And again, the RPM is fixed at 2,095. So for this particular fan, the corrected design at 15,000 CFM is now going to require a brake horsepower of 52.9 and an operating RPM of 2,261. So this represents an 8% increase in the RPM for the fan. Where that could be significant is it may or may not be possible to speed up the particular fan to that speed. It could have been selected with for example, a Class 3 impeller based upon RPM, and this RPM requires a Class 4 impeller. So it could require impeller replacement. It could also shift the operating point up into a more unstable region for the particular fan. So that's another thing that has to be looked at. Also, the required horsepower for the fan has now gone up by about 26%. Okay, so based on typical selection of a fan, original design was 42 brake horsepower. It most likely would be chosen with a 50 horsepower motor. Now our brake horsepower requirement to meet this particular flow and static pressure condition is now exceeding the capabilities of that motor, and so it would require increase to a 60 horsepower motor, assuming that the fan, again, could be sped up to that particular condition. So as related to the fan only, what are the best ways then to prevent system effects with the fan? So similar to ductwork design, the best way to prevent the fan-related system effect is to design for proper inlet and outlet duct lengths without nearby obstruction to flow. Because again, remember the catalog fan performance was based upon these types of conditions. So if you create a condition where you have obstructions or elements too close to the fan, that will affect how the fan itself operates. The intent is always to try to strive for uniform flow, both into and out of the fan, which is based on 100% effective duct length for standard industrial ventilation practices. So depending on what the velocity of the ductwork coming in or exiting the fan is, that determines what the 100% effective duct length would be. The higher the velocity, the more straight ductwork is required to produce a uniform profile. Transition in or out of the fan, that design is also important, and proper duct sizes with shallow angles should always be used. If more drastic transitions are needed based upon the location of the fan, they should always be located as far as possible from the fan inlet, followed by a straight section of duct into the fan. Same consideration applies to outlet transitions. You don't want the angles to be too large, and again, the duct sizes that are coming in or out of the fan should be relatively close to the size of the fan inlet and out connections themselves. So now we can take a look at some real-world examples. I'd like everybody maybe just take a few moments to look at the ventilation system that's shown in this photo, and then we'll follow up with a poll question. So the question is, based on the prior photo, what is the potential impact on fan performance due to system effects? Consider it not likely, minor, moderate, or significant. I'll give you a few seconds to answer that. Okay, good. Everybody pretty much indicates that it's either moderate to significant, which is, it's a relative. These are all relative terms, but it is definitely going to be in the upper range of problematic for the system, and we'll run through a few reasons why. The first thing I'd mention is that for a small system, there's nothing wrong with using thermoplastic pipe for ductwork. But people need to keep in mind that piping internal diameters vary with schedule. And so depending on what schedule of pipe that you pick, you might be using, when you call it maybe 6-inch pipe, it might not be 6-inch internal diameter. It could be 5 3/4, 5 1/2. Obviously, higher velocity increases friction losses, and they could be higher than expected because of that. But the first thing I noted here in this was the transitions coming out of these small tanks. They're very, very shallow, or I should say they're very quick transitions in terms of the length between the small pipe and the larger pipe. In this particular case, these are expansions, which it's not going to have necessarily a negative impact on the design, but expansions can actually provide a regain. And so when you design too drastic an expansion like this, you really lose the benefit of any pressure regain at that point in the system. The next is the use of elbows. As we talked about before, for branch connections, elbows are by far going to be the highest turbulent dynamic losses as compared to other types of branches, such as Ys. So all the branches in this particular system are Ts, and therefore are going to have higher turbulent losses. So next we'll talk about system effects. You can see from the boxes that there's quite a few areas in here where there's 2, 3, sometimes 4 obstructions, components that are located in the system in very close proximity to each other. On the left you have a damper, a T, and an elbow. In the horizontal section, you have 2 dampers, a T and another damper. Coming down towards the fans, an elbow and a T. And the yellow boxes indicate what I would call ductwork system effects that are potential and a problem in the system. And the red indicates the problems as far as connections to the fans themselves. Coming into the fans, in the left red box, we have a T, a damper, and an elbow, which is directly connected to the fan. The next box over, we have an elbow, a damper, and an elbow. I mentioned before that system effect calculations are typically based on 2 components in close proximity to each other. As you get more and more components in close proximity, the available information on loss coefficients really becomes limited. And so it's really hard to predict how these types of things will impact the overall system, except to say that they will have significant impact. So the picture on the left shows the elbow connection coming directly down and into the fan. The picture on the right is the cross-section of the valves. These are actually valves because it's piping that was used in this system. And you can see how much the flow is restricted. Even when the valve or damper, if you want to call it that, is fully open. The cross-sectional area that's available through that fully open valve is only about 40% of the duct diameter. So it makes quite a bit of difference in terms of increasing the velocity and causing turbulence in the system. So we'll look at another application here. These are obviously much larger fans than the ones that were in the prior example. We have 4 fans that are being operated with a common outlet plenum. First thing we'll look at here is the outlet design itself. The fans are top angular exhaust and then go into an angular branch connection into the overall duct plenum. The exhaust duct is much larger in size in the plenum than it is for the branch itself. So in general, although distance is always something that you can look at, in general that's a pretty good design. It shouldn't result in too much in terms of system effect. At the same time, putting 4 of them all tied into the main plenum and being as located as closely as they are, there is more potential for system effect due to the exhaust from one fan washing over the exhaust from another fan as it goes into that main plenum. So the fan on the end, the far end, probably has the least potential for system effect, and the fan closest in the photograph probably has the most potential for some impact of system effect. On the inlet side, not the best arrangement. We have an elbow that actually comes directly into the fan itself. You can see that there's a transition. The elbow is a different duct size than the duct above it, and the transition is fairly abrupt. It looks like 45 degrees. In this particular case, since the vertical distance is available, I'm not sure why a proper transition wasn't utilized. You could probably have used a 15-degree angle and still been able to fit it in exactly the same space. Also, the elbow coming in from the wall, excuse me, the elbow coming in from the wall, it looks to me like that could have been moved closer to the walls. The vertical section could have been moved closer to the wall, and a straight section of duct, maybe not 4 or 5 diameters, but a straight section of duct could have been located between the elbow and the fan, and that would have helped reduce any system effect. The one difference here from this photograph to the prior one is the size of the fans. These are much larger fans, much larger ductwork, which in the case of the ductwork, the pressure drops overall will be much, much less. And at the same time, the fans are designed with variable frequency drives. Typically, the fans are chosen to operate at some frequency, RPM point below the peak, so that they have room to move above that by changing the frequency and speeding up the fans. And they're also, there's 4 of them designed, again, with redundancy. So a system like this, because of the large ductwork, the lower pressure loss, the impact of system effects tends to be less noticeable. Small duct systems, like in the other one, with a fixed speed fan, are much more prone to system effect problems. So here's a third example. Again, 4 large fans. In this case, they're not tied into a common plenum. So the inlet duct itself, it's a nice straight run coming into the fan. It does have a transition, and the transition is an eccentric transition. Preference, again, would be to have a concentric transition there instead, just to try to get the most uniform airflow that you can, although I would imagine the impact on this would be very small. At the same time, though, to me, there's no reason for any impact on this, because that same transition could have been moved closer to the wall, and then a nice straight run of the smaller duct size brought in and connected to the fan. So hindsight is 20/20, but when you get to look at some of these designs, you can see that there are things that can be done even within the given space constraints that can minimize system effect. The outlet duct arrangement here is similar to the example that we talked about. We have 2 45-degree elbows and a section of duct in between. The section of ductwork is short enough that there will be some system effect due to that. It's hard to say if in this particular case, but noticing where the ductwork penetrates the wall, if they could have then, again, moved that position so that you come out of the fan, single 90-degree elbow, and then straight out through the wall, and whatever other twists or turns you have to make them farther away would obviously have reduced the system effect here. So to summarize, in a ventilation system, you will have system effects when components such as fittings, dampers, etc. are located in close proximity, because that will result in energy losses that are higher than the combined loss of the individual components. The system effects will also occur when components are located too near the exhaust fan, which is disrupting the optimum flow profile into or out of the fan. And system effects are the #1 cause for fan non-performance. For duct design, best practices summary. First, the most obvious, always utilize proper duct velocities. The higher the velocity, the higher the friction loss will be. Minimize number of turns wherever possible. When you do have turns, try to avoid sharp changes in direction. Where sharp changes in direction can't be avoided, utilize turning vanes to improve the flow pattern in the ductwork. Always avoid putting components in close proximity to each other. And then lastly, you always need to determine the potential impact of system effects when calculating the total static pressure that's required for the system. As far as the fan, similar recommendations as far as best practices. Always utilize proper duct velocities. Use sufficient straight duct on the fan inlet and outlet to provide uniform flow. Use proper transition angles for the inlet and outlet transitions where needed. If you have to use an outlet elbow close to the fan, one recommendation is always to position the elbow to at least match the spin from the fan so that you get that circular motion and minimize any loss due to the elbow. If you turn that elbow in an opposite direction and the airflow all of a sudden again has to turn 90 to 180 degrees from its original, then it's going to cause problems. And again, avoid putting components in close proximity to the fan inlet or outlet. Okay, so, well, sorry, we have a little bit of time left, not a lot, but
yeah, we've got, thank you, John. Appreciate that. We do have a couple minutes for some questions. We are running a little bit long, so we'll try and at least fit a couple in. But before we move on, just a reminder to everybody who is here for the professional development hours. The widget, the green one on the end, is your test widget. That is where you're going to take it. You need to get 8 out of 10 correct. Once you're done with that, you will go over to the yellow widget, and as long as you have completed all the requirements, watching, being on for 50 minutes and all the test requirements, there's a little button or a little squiggly square at the bottom. That is actually where you will print your certificate. We're going to answer a couple questions here, and then after that, we're going to go, we'll keep the platform live for 30 minutes after this webinar is ended. And that will actually give you all time to either print out resources, take the quiz, fill out our survey. We'd appreciate that, and just do anything else that you need to. If for any reason you need to leave, you can always come back to the on-demand version. Once we close out of this, the archive version will be available. It's basically the same link that you used to get on today. So we're going to move on to just a couple questions here real quick. And does the material of construction for the ductwork have a significant impact on system effects?
Well, different materials have different roughness coefficients, and so they will have different pressure drops. Now, in many cases, it's minimal, but probably an extreme example would be a system that used any type of corrugated flexible hose for air ductwork. The friction loss from that is going to be much higher than the friction loss from smooth ductwork. So in that case, if you combine that kind of system again with components, it's going to magnify the system effect. So yes, I mean, the smoother the surface of the whatever ductwork you're using, the less friction loss, and the impact of system effect will be somewhat less, but it'll be proportional.
If available space will not allow for the recommended 3 duct diameters at a fan inlet or outlet, can straightening vanes be used to reduce the necessary straight length?
Probably the recommendation, and we discussed putting it into this presentation, but we had a lot of material to cover. Recommendation would typically to try to be to use an inlet box. An inlet box that's properly designed can therefore bring a vertical piece of ductwork down into a fan at pretty close proximity. It does have, depending on the design of the box itself and the velocities, it can have turning vanes inside the box itself to minimize the space requirements.
One more, and we'll probably have to end this here. And if we didn't get to your question, don't worry about it. We will get back to you for sure. So last one. Is there a recommended safety factor that should be applied to all fan designs to cover for system effects, or do they need to be calculated specifically every time?
That's a real good question. The difficulty with, as you can see from some of these examples, of trying to calculate system effects every time is that in many cases, each system is unique, and depending how complicated the system can be, the availability of coefficients and the ability to accurately calculate system effect can be difficult. At the same time, one thing you have to be careful of, you want to guard against, is not over-designing the fan by too much. based on the specific fan, because that can then result in the fan not performing the way you would expect it to also. And also additional cost depending on how the fan was selected based on size and the fan size itself and the motor size. So I guess my answer is no. There's not something that we would recommend as a typical factor. You really have to look at it from system to system and then gauge the risk for the particular system, gauge the accuracy and ability to calculate the system effect versus the unknowns, and then determine what type of safety factor might be needed.
Okay, that's all we have time for today. Again, if you have any questions, we're going to be on the platform here for another 30 minutes, so feel free to continue shooting over Q&A, and we will get back to you individually, or we will get back to you after the webinar itself. And we just want to thank you for joining us and hope you found the presentation helpful, and we hope to see you again. Take care.